Okay. Hello and good evening to all of you. Good afternoon to all of you. My name is Nitin Tomar and I am a third year PhD student in the Department of Mathematics here at IIT Bombay. So, in today's session, or more like a discussion, we are going to discuss the fourth assignment of MA57 Complex Analysis 2021. Yes. So, in the first question, this the first question is I'm reading the first question. Let D denote the unit disk defined by this. So D is the unit disk of radius 1 centered at 0 in the complex plane, and del D denotes its boundary, which means the circle, okay, mod z equal to 1, collection of all those z which such that mod z equal to 1. Now which of the following are true? Okay, so the first part is, if you define dw, so what is dw? Here you have w and you take radius 1 from this center and you draw a disk. So everything inside is dw. Everything inside is dw. So the question that is being asked is about the following inequality, whether or not this this inequality holds. Mod of Ez is less than equal to e power mod w plus 1 for all z in dw. Okay, d subscript w. Now first of all we have to is this so I hope we know all of this. All There is this one inequality. If you take any Ez, now how does Ez look like? It looks like real part of z plus iota times imaginary part of z, right? Now if you take your mode here, if you take its absolute value, then it will be what? Mod of absolute value of e power real part of z. Because see, this will be e power iota theta and the mod will be 1. Okay, so okay, I'll write this will be e iota imaginary part, and this part has modulus 1. Okay, this part has modulus 1. So what we get is the following, that this is precisely equal to modulus of e power of real part of z. Now we know exponential is a positive function, so exponential is a non-negative function, so it will be same as e power real part of z. And exponential is increasing function, right? So it will be less than equal to mod of real part of z, because real part of z is less than any number is smaller than its modulus, right? So we'll have this inequality. Is this inequality clear to all of you? And because real part of z, sorry, any real part of z is actually less than equal. So here in the last we have used real part of z is less than equal to mod z, and because exponential is a monotone function, monotonically non-decreasing function, hence we have this inequality. Okay, is this fine? I guess yes.
Yes, fine.
So what do we get basically? So we'll use this inequality time and again, that e power z modulus is actually less than e power mod z. So now look at this. If z minus w is less than 1, then this is possible. Then I can write z to be w plus r times some alpha, where alpha has mod 1 and r is less than 1. Why? See, because if mod z minus w has absolute value less than 1, then what does it mean? That it is of this form, right? R alpha, where R is strictly less than 1 and alpha is in the circle del of t. And from here you will get z can be written as w plus r alpha for some r less than 1 and mod alpha equal to 1. Now we use all of this, okay? So mod of e power z is actually equal to mod of e w plus r alpha. Now e w plus r alpha can be written as mod absolute value of e w times absolute value of e r alpha. And here we will use that absolute value of ez is less than e of absolute value of z. So each of them I have used for EW and e power r alpha. Now what is this? Modulus of r alpha is what? R is a positive number. R is a positive number, okay? R is a positive number. Or it need not be. You just take mod r, okay? Times mod alpha. Yeah. Here you can write mod r less than 1. Yes, please correct this. This can be written as mod r less than 1. Now, this mod alpha, because it is in circle, so it is mod r, okay? So this is precisely mod r, okay? But what is mod r? Mod r is chosen such that it is less than 1, so hence we have this inequality. Is this clear? Okay, so this inequality holds for all z in d subscript w. Now next question is interesting. It says if d is a holomorphic function, so here is our d, and see this cut boundary implies that the boundary is not included, okay? D is the inside of this, so this is my d, and f is a holomorphic function on this d. F is a holomorphic function on unit disk. Now suppose some omega is in d, so omega lies inside d, so omega is of something like this. Okay, something like this, so this is omega, okay? Omega is something here, so this part is omega, such that omega bar intersection with the boundary of circle is empty. So what does this mean? What does this mean? If omega is contained in d, this implies omega bar is contained in d bar, right? Now d bar can closure of d can be written as union of interior, which is open unit disk, and its boundary, right? But it is given that omega bar has empty intersection with the boundary of circle, so this part won't be there. So we'll have omega bar is contained in d. So I have written this only up until now, that omega bar is contained in d. This we have concluded. Now the question is f bounded on omega? See, we know that f is holomorphic on d. So f is holomorphic on omega bar, right? Now every holomorphic function in a domain is continuous by definition, right? Holomorphicity, what do we mean? It is differentiable at every point in the domain. And differentiability implies continuity. So f is continuous on omega bar. Now what is omega bar? Omega bar is contained in d, therefore it is bounded. Right? Omega bar is contained in open unit disk, so it is bounded. And because we are taking closure of omega, by definition, closure is a closed set. So omega bar is a compact set. And we know continuous image of a compact set is compact, hence bounded. So f of omega bar is bounded. So on omega it is automatically bounded, right? Because if on omega bar it is bounded and omega is a subset of omega bar, therefore it has to be bounded on omega as well. Okay, is this clear? See, you can tell me if something is not clear to you guys. Okay, just stop me there. Complex set is compact. Yeah. Now next question is F is holomorphic on omega where D bar is contained in omega now. Okay, now so you have disk, closed unit disk D bar, and you have some open set. I don't know the open set, but it is, oh God, it's a terrible color. And you have some omega here. Okay. Now f is 0 on the boundary of D, which means on these points on the circle f is 0. Then can you recall any theorem which can say f is 0 on the, you recall identity theorem. So what does identity theorem says? If, okay, I have written down. So identity theorem says that if f is a holomorphic function on some domain omega, it is omega, number 1, and zero set of f, zf, okay, zero set of f has a limit point in omega, has a limit point in omega, then f is 0. Which means the points on which f is 0, if it has a limit point in omega, then f has to be 0, no other choice. Now see, on this circle f is 0, and circle is a closed set, right? So it has all its limit point in omega. So 0 set of f, which is contained in the circle, has a limit point in omega because d bar is contained in omega. So by identity theorem, f has to be 0 on the whole of omega, in particular because d closure is contained in omega. So on D also it has to be 0. Is this clear? All we have used is identity theorem, okay? All we have used is identity theorem. Yeah. Now, again, there is this one question from the identity theorem. Using the identity theorem, we can kill it. Suppose S is the open unit square, S is some open unit square with real part of Z and imaginary part of Z is less than equal to 1. And del S be its boundary. Now, if two entire functions, see entire functions, okay, f and g agree on its boundary, then f and g agree everywhere on S. Okay. So how does this question look like? Where I can draw the image? Yes. So this is my complex plane, and S is some square. Okay, S is this square, and on its boundary. So this is my boundary, right? This is my S. This is del S. On its boundary, f takes zero values. Now by again identity theorem, because f so f and g agree on so you consider the function h equal to f minus g. Okay. Now f is equal to g on the boundary of this square, which implies h is equal to 0 on the boundary of this square, right? Now again by identity theorem, because h is entire, because f is entire, g is entire, so is their difference. So h is one entire function which is 0 on the boundary of some set. Okay. And anyhow it will have limit point in complex plane. Okay, see the domain is we need a domain for identity theorem, and in this question the domain is the entire complex plane. So by identity theorem, h has to be 0. Identity theorem implies h has to be 0 on the complete complex plane, which means f equal to g everywhere on the complex plane. Okay, so is this clear?
So
So
doubt, sir.
doubt, sir.
How you
How you
take
take
h
h
equal to
equal
f
to f
minus
minus
g?
g? Huh?
H
H
equal to
equal to,
how you
how you
take
take
h
h
equal to
equal
f
to f
minus
minus
g?
g. See what we have. See identity theorem says if a function is 0 on some set which has accumulation, if which has limit point in the domain, then the function will be 0, right? You agree with this?
Yes.
Yes. Now you have to show f and g. If f and g agree on some square boundary, then f and g are same everywhere. Okay.
Okay.
Okay. So you just construct a artificial function hz equal to fz minus gz. Okay. Now what will be its value on the boundary of the square? Can you tell me? What is the boundary value of hz? It will be 0, right? Because f and g agree on boundary. Agree means they are same.
Okay.
Okay. Now if they agree on the square, by identity theorem hz will be 0 everywhere on C. Now you just plug back the values. What was hz? Hz was fz minus gz. So this implies fz minus gz is 0 on C. Okay. So which means fz equal to gz on C, therefore in particular on S. Is this clear now?
Yeah.
Yeah. Okay. So you must have learned identity theorem, right? Have you? Have you guys? Do you know identity theorem? Okay. Now the question is, if f is a holomorphic function, if f is a holomorphic function on some domain omega, then their infimum value, what is this? Yeah. So if f is a holomorphic function on some set omega and closed unit disk is contained in omega, then infimum of modulus of f of z over z varying over this open unit disk, it is same as the infimum of modulus of fz z varying over the boundary of the open unit disk. You must have seen some similar kind of statement for the supremum, right? Have you seen? Okay. Okay, so the question is, are these two numbers equal, right? First of all, why these numbers should be existing? Because f is a continuous function, f is a holomorphic function, so therefore it will be a continuous function also. And a continuous function on a compact set attains its bounds, right? So infimum is also a bound. So these numbers will be there. These numbers will be some finite number. Now you choose fz to be z. If you choose fz to be z, what will you get on left hand side? What is the infimum of mod z over open unit disk? Can anyone tell? I mean, it's already written there. It will be 0, right? Because mod z is always greater than equal to 0, no matter what. And at z equal to 0, it attains this value. So this value is 0. Now, what about the right hand side? If fz is z, then what will be the value of mod z, where z comes from the circle? If z is coming from the circle, this mod z always be 1, right? It will always be 1. So its infimum will always be 1, right? So but does 0 equal 1? No, right? This is a contradiction. So this statement does not hold true. Okay. Now, now the same thing is asked. Again, the same question is asked with the condition, that f does not vanish on d bar. Note that in the question number 5, the same question was asked, except without the condition that f does not vanish on closed unit disk. Now what do we do with this information? Remember that in part 5, the example that we constructed, it was vanishing on d bar, right? At z equal to 0, it was vanishing. So this example we cannot take in part 6. So if f does not vanish on d bar, I can construct 1 upon fz, right? It is well defined. The only point of problem, or mathematically we say, the only point of singularities are where fz can be 0. because then 1 upon 0 will not be defined. So if gz is 1 upon fz on d bar and f does not vanish, what does it mean does not vanish? It means fz is never 0. Fz is never 0 on d bar. Okay. Does not vanish means this. Fz is never 0 on d bar. So this g is a well-defined holomorphic function since f does not vanish on d bar and f is a holomorphic function. So therefore, this g is also holomorphic. Now, one thing you should note that infimum of mod z, it is supremum of mod gz, right? Because one is the reciprocal of the other. If f attains its maximum value at some point, then 1 upon maximum 1, if see these are two functions, right? This is my gz. If f is maximum at some point, then 1 upon f will be minimum at that point, right? Yes or no? Hello? Okay, Ravi, thank you. Yes. So I can write this as infimum of mod of fz will be same as supremum of mod of gz, which is 1 upon fz mod. Now, we can use the maximum modulus principle. So maximum modulus principle says supremum of a holomorphic function which is continuous on its boundary of domain, that supremum is always attained at its boundary, right? Here we have z belongs to d, and here we have z belongs to del d, which is the boundary. Now again using that trick, we can replace this supremum over the boundary by infimum over the boundary when we replace g by f. So from here to here, this is fine, right? And this is what we needed. So this is completed here. If you have any doubt in any part, please ask. Then I'll move further. Please, if you have any doubts, then just tell me. Okay. Now, which of the following statements are true? First, given this function, this fancy looking function, it is harmonic on this domain mod z minus 1 is less than 1. So, what is this domain? You have 1 here and you take radius 1. So, it will be this circle, right? So, it will be this circle. So, this is my domain. This is my domain. Yes. Now, what does harmonicity means? Harmonic means uxx plus uyy is 0. One can check this, right? You just take, you find partial derivative of x, then again you derivate with respect to x. You find partial derivative of u with respect to y, and again you derivate it with respect to y. You check whether these two, when upon adding, is giving you 0 or not on d1. One can use this. This is a simple going trick, right? Without any confusion, we know how to differentiate. Okay. Exactly. Manik, Menak, or if I'm pronouncing your name correctly, this is exactly, this is called Laplace equation. So you can check it. Or another way to see is this: we know if f is an, okay, I'll say, yeah, if f is an analytic function on some domain, if this is an analytic function, then you know f has two parts: one real part and one imaginary part. U is called the real part of f, and v is called the imaginary part of f. And you know that this satisfy Cauchy-Riemann equation, right? Ux equal to Vy and Uy equal to minus Vx. Now can you tell me what will be Uxx? It will be Vyx, right? 1, 2. So 1 imply this. Second imply if you derive with respect to y, then it will imply minus vxy. Now from your calculus class, you know that if v is a continuous function and its partial derivatives are continuous, then vxy equal to vyx. Because why? Because v is continuously differentiable function. This is a result from calculus. V is continuously differentiable functions. So now when you add uxx plus uyy, it is vxy, because this is actually vxy minus vxy. So it will be 0, right? And similarly, you can prove that vxx plus vyy is 0 using the same trick. So what I want to say, if f is a holomorphic function on a domain, then its real part as well as imaginary part are harmonic. Okay.
So
So,
one
one
second.
second. Yes, yes, yes. Please ask. Yes.
Yes,
Yes.
previous
Previous
slide.
slide. Okay. Yes, this one.
The
The
one
one
implies
implies
uxx
uxx
equal to
equal to
vyx.
vyx.
This
This
implies
implies
v
v
equal to
equal to
xy.
xy.
So one
So one
second, I'll
second, I'll
explain
explain
how
how
uxx
uxx
equal to
equal to
vyx.
vyx. See, you derivate this with respect to x and with respect to x. You will get this, right?
Okay,
Okay.
okay,
Okay,
thank you.
thank you. And similarly, if you derivate this with respect to y, you will get y here and y here, right? Yeah. Okay. So we can use this because we are learning analytic function theory. Is my screen? Why is it not coming? No, I have opened my PDF here, but somehow it's not being shown. Can everyone hear me? Hello? Am I audible?
Yes,
Ah,
sir.
yes, sir. Ah,
Yes.
yes. Okay. Now you see this uxy is nothing but x minus 2 upon x minus 2 square plus y square. Okay. So you just calculate all these steps to realize that this uxy is actually real part of 1 upon z minus 2. This is one easy calculation, right? You can do it. Or should I do it? You calculate real part of 1 upon z minus 2 and you will get your u. So, but we know that this function 1 upon z minus 2. So, where is the point of singularity? At 2, right? But does 2, so there is 2, here is 2, but 2 does not belong to the disk, to our domain. So 1 upon z minus 2 is analytic on d1. It is holomorphic on d1. So because u is a real part of harmonic function, real part of holomorphic function, hence it is harmonic. Or directly you can see it via the Laplace equation. Anyhow, okay. Is this clear? Okay. Let's move ahead. So read the second question. I think I'm lagging somehow. Let me check my Wi-Fi. Am I audible? Am I audible? Ah,
Yes, sir.
yes, sir. Actually, I think some internet issue from my side because it's raining. Okay, just bear with me. I'm really sorry. Now, please read the second question. Let f and g. So, just read the second question. Let f and g be two holomorphic function. defined on an open connected subset omega such that their real part agrees. Does that mean fz equal to gz for every z? This is not true, right? If you take fz to be say iota and gz to be some, let's say, minus iota, they are holomorphic functions, right? On any domain, they are constant. So constant functions are holomorphic. So fz and gz are such that their real parts agrees. Both of them have real part to be 0. But are they same? No, they are not same, right? So this option is false. Now, second question. Now the next question is same, except the conclusion has been fz minus gz is a purely imaginary constant. Just a minute. Yeah, fz minus gz is a purely imaginary constant. So again, like use that trick. Hz, you define hz to be fz minus gz, and this is holomorphic, right? Why? Because f is holomorphic, g is holomorphic. And what will be its real part? Can anyone tell me? What will be the real part of h of z? It will be real part of f minus real part of g, which is 0 on omega. It is given. So h is a holomorphic function so whose real part is 0, which means h is iota times imaginary part of iota times imaginary, right? I mean, one can write hz as real part of h of z plus this, but real part is 0, so it is iota times imaginary part of z. So h is a so this implies iota h is minus of imaginary part of h of z. Sorry, I'm writing h. So this iota h, it is a real valued, some Wi-Fi. Just a minute, guys. Hello, am I audible? Hello, am I audible?
Yes.
Okay, thank you. So where was I? I was saying this h is, h takes only iota times h. If you transfer this iota here, you will get iota times h is imaginary part of h. But imaginary part of h is a real number, right? So this iota h, this iota h is a real valued holomorphic function. And we have learned that any holomorphic function which takes real valued on a domain, it has to be constant, right? So this h of z must be constant, because if iota h is constant, you transfer iota on the right hand side and you're multiplying by a constant, so everything will be constant. So h of z must be constant on omega. And what kind of constant? Imaginary constant, right? Purely imaginary constant, because real h has no real part. So so this and what was h? H was f minus g. So this implies that f minus g is a purely imaginary constant on omega. Okay. So is this fine? Okay. Now the harmonic conjugate of a given harmonic function u on omega is unique. First of all, let's recall what do we mean by harmonic conjugate. A harmonic conjugate of a given harmonic function u is a function v. So if you have a harmonic function, okay, v is called is harmonic conjugate if u plus iota v, this is a holomorphic function. Okay, if this is a holomorphic function. Is this clear? The definition you must be knowing. So is this unique? The answer is no, right? Because if V is a harmonic conjugate, if V is a harmonic conjugate, what does it mean? U plus iota V is holomorphic. Now you add any constant, U plus, let's say V plus 1, then this is also holomorphic, right? Because you are just adding one constant. Let's say you add V plus 1. Instead of V, you choose V plus 1. Then U plus iota V, and this will be iota. So this is holomorphic because we have chosen V to be harmonic conjugate, and you're adding one constant. So harmonic conjugate is not unique. Is this clear? So what I want to say, if V is a harmonic conjugate of U, then V plus C is also a harmonic conjugate of U. So by no chance they are unique. Now the second result addresses that if V is a harmonic conjugate of a harmonic function, then U minus V has, if such that if U minus V is constant. So you have a function, a harmonic function U. You have its, uh, then we have V as its harmonic conjugate. What does it mean? That U plus iota V is holomorphic. This is a holomorphic function. But we have been given that U minus iota V is a constant, let's say C. So what does this, so if this function is F, so what does F become? F becomes C plus V plus iota V, which will give you, yeah, okay. So this is C plus 1 plus iota times V, okay. Now see, you can write this V as F minus C upon 1 plus iota, right? Now F is holomorphic, so F minus C is holomorphic, and 1 plus iota is holomorphic. Like it's a divide, we are dividing by 1 plus iota, so this is holomorphic. So V is a holomorphic function. But what was V? V was a harmonic conjugate, so it was real valued function. So V is an analytic real valued function on omega. So it has to be constant, right? It has to be constant. So V is constant. V is constant. And what do we have to show? That this U has to be constant. Now, if now, so yeah. So f is a holomorphic function U plus iota V, but V is a constant. So let's replace. So let's say V is alpha. Okay. Now, what can you say about the functions whose imaginary part is constant? Imaginary part of f is constant, right?
Real
Real
valued
valued
function.
function.
Yeah, that is one result. If f is a holomorphic real valued function, that function has to be constant. Now, there is one another result which says, okay, let me just do here. If f, again, these are some basic facts. If f on omega to C, it is some holomorphic function such that imaginary part of f is constant, then you can use Cauchy-Riemann equation, right? This is a domain. To say that f is constant. So this implies f is constant. Now if f is constant, so its real part will always be constant, right? So using this result, we can say that because u was the real part of f, so u has to be constant. Okay. Now the next question. If you have any doubt, then ask. So this next question is all about calculations. So you know what is GL2C? It is a group of invertible matrices, 2 cross 2 invertible matrices, whose entries are from the complex plane. Now, it says if you take any alpha from A, B, C, D from GL2C, so this alpha from GL2C, A, B, C, D, where C, then C comma D, they cannot be 0, 0, right? If both of them are 0, then this will become 0 and alpha will not be an invertible matrix. So both of them cannot be 0. Now, with this information, the question is corresponding to every alpha, which is A, B, C, D, we define a map. Let's say phi alpha Z is, or we say that like alpha of Z is AZ plus B upon CZ plus D. Okay. Now, because C and D both cannot be 0, so this map is defined, and so you must have seen this Morbius transformation on the extended complex plane. Now the question is whether this holds. So what do we, so alpha beta is again one matrix. So you check all these calculations. So what if my alpha is A1 B1 C1 D1 and my beta is this? You know how to multiply two matrix. So my alpha beta will be this matrix. Now how does Z acts? How does this matrix X acts on Z? So this first coefficient is A1 A2 plus B1 C2. So multiply it with Z and second as it is. So you is this is just computational. Okay. I am stopping here for 30 seconds. You please see what we have done here. If you have any doubt, then please ask. Okay. If you have any doubt, please ask. So if there is some confusion in this notation, let me explain. What does this alpha dot beta dot z mean? This means, see this is A1 B1 C1 D1. Now this dot means there is one another matrix A2 B2 C2 D2 dot z. So it will give you some W, right? What it will be? It will be A2Z plus, this will be A2Z plus, so this will be A2Z plus B2 upon C2Z plus D2. Hmm? So what does this mean now? A1 B1 C1 D1 dot W, where W is this entire number. Now what it will become? A1W plus B1W, sorry, plus B1, and C1W plus D1. Now you put the value of W. It will be A1 of A2Z plus B2, C2 of Z plus D2 plus B1. So it is like composition, right? It is exactly the composition, isn't it? And then C2Z plus D2 plus D1. And you solve this and you will find that these two entities are equal. Okay. Any doubt? All this is computational. Okay. I mean, so now question is, if you multiply by scalar, does this value comes as it is? So let us compute this LHS. What is LHS? 2 alpha dot Z. So if our alpha is AB and CD, what will be 2 alpha? 2 alpha will be 2B, 2A, 2B, 2C, 2D. And how will it act on Z? It will act as 2AZ plus 2B, 2AZ plus 2B upon 2CZ plus 2D. And you will see that every 2 cancels out, right? You can pull 2 out of the numerator as well as from the denominator and they'll cancel out. So you will get Az plus B, Cz plus D as it is. And this is same as alpha dot Z. And this is not equal to 2 times alpha dot Z, right? So this option is false. Now the third question is long. So SL2R, basically SL2R means this SL2R. It is again 2 cross 2. It is the collection SL2R. It is the collection of A, B, C, D 2 cross 2 matrix such that A, B, C, D they are coming from R. Okay. And its determinant. What will be the determinant? AD minus BC, right? This will be the determinant of this matrix. It is 1. Okay. So our SL2R is this. And it is a subset of GL2R, right? Because for GL2R we need determinant to be non-zero. In particular, it can be 1. So yeah. So the question that has been asked here, if you take alpha dot Z, we know its action. So its imaginary part is positive if and only if imaginary part of Z is positive. Let us see. So first of all, what will be our alpha dot Z? It will be if our alpha is A, B, C, D. Okay. Then alpha dot Z will be Az plus B upon Cz plus D. Now you know how to compute the imaginary part, right? Imaginary part of alpha dot Z, which is imaginary part of Az plus B. Now what do? You multiply it by conjugates. So because A, B, C, D are real, okay? So please remember that we'll multiply it by C. Okay. We'll multiply it by Cz plus D bar. So it will break. C bar, Z bar plus D bar. But C and D are real. Okay, everything is real, the coefficients. So it will be just Cz. So it will be just Cz bar plus D upon Cz bar plus D. Okay. So this is what we have done here. So from here to here it is clear. Now you multiply it. So in the denominator you will get mod of Cz plus D square, right? So in the you will have this, and in the numerator you will have AC ZZ bar plus BC Z bar plus ADZ plus BD. So again, this is very computational. What we are doing, we are computing the imaginary part of alpha dot Z. Now see, this ZZ bar is mod Z square. Okay, so finally we replace, and if we write Z as x plus iota y, we plug in the values here. So Z will be x plus iota y, and Z bar will be x minus iota y, and we'll get this. And if you collect the imaginary part, it will be AD minus BC y, right? And everything is real because AD, BC, everything is real. So finally, can I say, if you look carefully, so imaginary part of this big bracket is just this part, AD minus BCY, right? And what was Y? Y was imaginary part of Z. So from this calculation, can I say this? I can say this, right? Now everything is clear because because alpha was in SL2R, so this AD minus BC, it has to be 1. So we get this. Now you see this 1 upon mod CZ plus D square, this is always positive, right? Why? So this implies, just a minute, if CZ plus D. Yeah. So you see, you are able to write imaginary part of alpha dot Z as some positive number. Let's say, what should I use? Let's say A, or okay, okay, so this is a positive number. Okay, now imaginary part of z, if it is strictly positive and it is also positive, so product of two positive number is positive, right? So this imaginary part of alpha dot z is positive, and the vice versa also holds with this relation. So this thing is clear or not? Is this clear? Okay. Now fourth question: if imaginary part of z is positive, then there exists alpha in SL2R, which is such that alpha dot I is z. Now what we have to do? We are given some z whose imaginary part is positive, and we are given z equal to x plus iota y with y positive. Now we need to find alpha ABCD in SL2R such that alpha dot I is z. See, the thing is, I can directly write one alpha which will satisfy this equation, but we are here to see how is this possible, how that example is coming. Okay, so in the previous part we have, if you know, that we computed this imaginary part, right, for SL2R, just in the above part. And if you look at the other part, this part was left, right? So this is this corresponds to the imaginary part of alpha dot z, and this corresponds to the real part of alpha dot z. So I have just written down these two part. Okay, see, what is my problem? I have to find this A B C D using z. Okay, so the best thing I can do is, because alpha dot I equal to z, it is given. Now what does this mean? That real part of alpha dot I plus iota times imaginary part of alpha dot I is equal to real part of z plus iota real part of y. So this implies real part of, so I can, to start with, I have these two things equal and these two things equal, right? So why not start with this piece of information? And this is what precisely we are doing. So with this, now in our case, w is equal to iota. So if w is equal to iota, this real part of w is 0, right? And this mod w is 1. So we'll get AC plus BD, and this part will cancel because everything is 0. Real part of w is 0. So we're left with this AC plus BD upon CI plus DI mod square. Now, because we are in SL2R, this AD minus BC is 1, and imaginary part of iota, W is iota, remember, its imaginary part is 1. So we'll have that imaginary part of alpha dot I is this. So that is too much of redness. Okay, let's delete this. Yeah. Now we can use this equation alpha dot I equal to Z, right? So the real part must be equal. So what was the real part of Z? It was X. So this equation holds. And similarly, this equation holds because Z was, remember, X plus iota Y. Now we just need to choose value correctly. Okay, you just choose C equal to 0. Now if C equal to 0, that means D cannot be 0. Why? Because if C is 0, remember A, B, C, D. If D is also 0, then determinant of alpha will be 0. But we need determinant of alpha to be 1. Okay, so D cannot be 0. Now put C equal to 0 in this, and you will get X equal to BD upon mod D square, but D is a real number, so mod D square will be D square. And similarly, when you put C equal to 0 in for Y, you will get D square. So you get this. Now this implies you can choose D to be 1 upon root Y. I mean, it will be plus minus 1 upon root Y, but you choose 1. Okay, and this is nothing but B by D. So you can choose so you can choose so from here X equal to XD equal to B, but sorry, b equal to xd, and what was d? It is x by root y. Okay, and AD minus BC equal to, so now we have C equal to 0, D equal to 1 by root y, and B equal to x by root y. Now what you have to choose? You have to choose only A. So we can use this relation, right? AD minus BC is 0. Now because C is 0, it will imply AD equal to 1, so which implies 1 A equal to 1 upon D. So you can choose 1 upon D is root y. So this alpha works, okay? And C, because y is positive, so you can take square root y as well as 1 upon square root y. So everything is defined, and this alpha works, okay? So this option is true. Now the fifth question is, if two complex numbers whose imaginary part is positive, there exists alpha in SL2R such that alpha dot z1 equal to z2. Now we have seen that if imaginary part of this is positive, so by previous part there exists one alpha 1 such that alpha 1 dot iota is z1, right? By part 3. And imaginary part of z2 is positive, which implies alpha dot iota is z2. Okay. And this implies that iota is actually alpha 1 inverse dot z1. Now you choose alpha to be alpha 2 alpha 1 inverse. Now what will be alpha dot z? It will be alpha 2 alpha 1 inverse dot z. And we have proved that it can be split like this. Now what is alpha inverse z? It is iota. Sorry, z1. Z1. Yes. So alpha inverse z1 is iota. And what is alpha 2 dot iota? It is z2. So you have proved that alpha dot z1 is z2. Okay. And because alpha 2 was alpha 2 alpha 1 inverse, its determinant will be, determinant of two matrix is just determinant of the product of the determinant. And because alpha 2 has determinant 1 and alpha 1 has determinant 1, so its inverse will also have determinant 1. Okay, so this alpha that we have chosen, this indeed belongs to SL2R. Okay, so this question is done. We're running out of time, just give me 10 more minutes. Okay, now this question is, if alpha belongs to SL2R such that alpha dot iota is iota. Now what does alpha dot iota means? Az plus b, sorry, alpha, if alpha is ab plus, so let alpha is a b c d. Now what is alpha dot iota? It will be ai plus b upon ci plus d. And if it is iota, then ai plus b is di minus c, right? Cross multiplication. Then imaginary part you compare, then a equal to d and b equal to minus c. And because it is in SL2R, then AD minus BC equal to 1. So A equal to D means A square. Minus BC will be plus C square. Or you can take B square equal to 1. So this A square plus B square equal to 1 means A comma B is a point on the circle. And every point on the circle looks like sine theta, cos theta, sine theta, right? So if A equal to cos theta, then D is also equal to cos theta because A equal to D. And if b equal to sine theta, then c has to be equal to minus sine theta. And this is what we have proved. Is this clear? Now all the questions are easy after that. I mean, they are not long. And this took too much time. Now z1, z2, z3 are non-collinear points. So z1, so they lie on a circle, right? Any three non-collinear point, there is a circle, unique circle passing through them. This circle is denoted by gamma here. Yes. Yeah. Starting at z1. Okay, so z1 is the starting point. Now let phi be the Mobius transformation. So this phi is a Mobius transformation that maps z1 to, okay,